Assalamu alaikum dear students, we're back with another video lesson. Remember, we're still in chapter 7. In the previous video lesson, we did talk about interference. We said two waves will interfere whether constructively or destructively. That depends on the phase difference between the two. But something more important than that, for the two waves to interfere together, they must have the same wave, the same frequency, you can say, or the wavelength too. So if that is the case, then we can say they will interfere constructively if, of course, the phase difference between the two is 0 or 360 or is multiple of, you can say, of a wavelength. That is one aside. And of course, we said on the other side, we have destructive interference. There were two parts. Yeah? We said there is either weakening interference or there is complete, you can say, total destructive interference. It is weakening if the two waves or the phase difference between the two waves is 180 degrees. But then there is a difference between the amplitude. Let's say the amplitude of one of them is 3 units. Let's say the amplitude of the other one is 2 units or 1 unit. As long as there is a difference between the two, the resultant wave will be, you can say, or the resultant wavelength will have an amplitude that is smaller than the amplitude of the larger wave, you can say, or the wave with a larger amplitude. That would be more correct to put. Okay, and then for complete destructive interference, we said the phase difference between the two must be 180, that's one, and then of course they must have the same amplitude as well. Once these two happen, of course, regardless to that, the waves must have the same, let's say, wavelength, then of course we get a complete destructive interference. And of course, if we, let's say, put that on the screen, we will see a dark spot or a dark fringe on the screen that is resembling a destructive or complete destructive interference. We said for constructive, we will see a bright, let's say a bright light on the screen, whether if it is a, let's say, monochromatic light, or it could be a bunch of colorful colors that we see, as long as it is bright, let's say. And then of course we ended up right at this point here. And now we said that if we have, for example, lights, and if we allow the light to pass through slits, let's say, and then we allow them to fall on the light, on a screen, of course, we get different regions of, let's say, dark regions, and of course, bright regions. We said we call those bright regions, we call them constructive interference. The dark fringes, we call them destructive interference. And of course, we give them some, let's say, numbers as well. We said those numbers are called order of magnitude, and these are measured according to the central maxima or according to the brightest fringe that we have, which is right in the middle of the screen, you can say. And then we ended up right here. So now we can say some of the ways that two coherent waves leaving the slit can combine at a viewing screen here. So basically this will be sort of the repetition of what I have explained last time, but I'll go through it just one more time to say why or how we get bright, let's say, fringe, and of course dark ones too, let's say. So let's say this is the screen that we have, and let's say this is the two slits, or you can say the two slits that we have. So this is, let's say, the one that is central maximum, that is the brightest, okay, according or among all the other fringes that we have. So we can call this one, the brightest one is basically M is 0, that is the central, or you can say 0th order of maxima, you can say. Okay, so now either one, if we take the one that is, or the next bright one, don't forget, because the one right next to this one is dark here, but if we take the bright one here, so let's say this is a bright, let's use this one here. So what happens exactly here? We said, imagine this, so light will be traveling from this, and of course it is measured, or you can say it is traveling a distance, let's say L1 here. That is basically the distance traveled by this wave here. And then of course the distance traveled by the other one here, let's focus on the central first before we go to this one here, because I think we jumped very quickly to this. Now if we take this one here, you can see that the distance that, or the light that travels from this one here, as you can say, these two the same thing here. So we can say if this is L1, this is L2, when they arrive here to the center of the screen here, or to the central maxima here, you can see that these two waves have traveled equal distances. And of course we'll say the phase difference between the two is 0. So we get a bright fringe right on the middle of the screen that is called the central maxima, or you can just call it M0 here. What about for the one that is, let's say, the one that is right next to it? For the one that is right next to it, if I let's say, take away this one here. So I want you to focus on the first one here. So light travels, for example, a distance, let's call it L, L1 here to this spot right here. That is the first, you can say bright here. So let's call it M1, yeah? Okay, and then, but for the other one, you can see that because it is closer to this one, far from this one. So this one clearly has to travel some extra distance here. So if this one, let's say travel just enough distance, let's say this is the same, plus one wavelength here, then of course, once the two waves arrive here, they're in phase, of course, we get another constructive interference here. Now that is the same thing if it is this side or this side, but if it is below, the other, or you can say the light that is coming from this slit has to travel, let's say, an extra wavelength here. Okay, so they cover or they travel the same distance, but for this one, because it is further, so it has to travel one extra wavelength. Once it is one extra wavelength, the light arriving at this 2 point are in phase, and of course we get a constructive interference here again. And of course, what about the one next to this one here? Once again, the light arriving from this one here, you can call this one L1 again, and for this one here, because that was one wavelength, so for this one, the light from this has to travel 2 extra wavelength here. So this is going to be L plus 2 lambda, and of course so on and on here. That is for both up and down, but like I said, if it is down, this one has to travel the extra distance, which is either 1 wavelength, 2 wavelength, or you can say it is a multiple of wavelength here. Now that is, once this happens, we get bright fringes on the screen here. Okay, so this is M1, you can say M2, and of course, according to the central. And then we have, you can say M negative 1, 2. We said those negative were just to tell you the arrangement of these according to the central bright one here. What about for the dark fringes here, which is also very important? So based on this, we can have, or we can drive an equation. We can say d sine theta, okay, it is equal to m lambda here. Okay, now this d basically tells you the slit separation here. This sine theta, that would be the angle, we can say, the angle starting from the central maxima to where we have this one here. So I think it's a bit messy now. Okay, so let me see if I can clear it up just a little. Or maybe I can do this one would be best. Okay, so that is what we have. So you can see these are basically the central maxima, that is, let's clean this. Okay, so this is basically the central maxima, you can see. So we have, that is d, the slit separation, basically. Okay, sine theta, that would be the angle between the central maxima, and of course you can say between the light as well, that is this angle here. Let's say for the first one and all that, okay? That is also can be called the path difference as well. We can call this one path difference. Okay, and then equals to m times the wavelength here. This m, of course, represents or indicates the order of magnitude for, let's say, whether the bright or the dark fringe here, but here we're focusing on the bright one here, so this is the equation. So we will get bright spots or bright fringe as long as we can say m is a multiple of a wavelength, you can say here. So of course m can be what? M can be 1, let's say, it can be 2, and of course it could be 3. You can say as long as it is a whole number, multiple of this, we will get bright fringes here. What happens if we have dark fringes here? So if that is the case here, let's use the same. Once again, we have a screen here. So here's what we have. This is basically still the slit separation here. This is the central maxima, you can say. Now, right next to this one, of course, we get a dark fringe here. So let's make this one black in here. And of course, another black as well. Okay. So what happens exactly when we have this? You can see that, let's say, when the light from one of these is arriving at this point here, so let's say this is L, you can call it L1 here, okay? So what about this one? When the light is traveling from this one here, when the light is traveling from this one here, it is traveling the same distance L plus half a wavelength. Remember, if it is half a wavelength, that means the phase difference between the two is 180 degrees, because remember the entire, or one wavelength, it is 360, or you can say it is 2 pi, yeah? Okay, so if it is half a wavelength, you can say the phase difference becomes 180 degrees, or you can say 1 pi. If that is the case, then these two waves, when they arrive at this point here, one of them is going to be like this, the other one is going to be like this. If that is the case, of course, they will cancel one another out, or you can say they will interfere destructively. And if they interfere destructively, there is no bright spot, is going to be a dark spot in here. So we can use an equation for this. We will say d sine theta, this is for the dark fringes, you can say, d sine theta, it is equal to, we can say, by the way, I forgot to mention positive or negative here, because m could be positive if it is above negative or there, but we don't take the negative ones here, just for the sake of to know which side it is of the, according to the central maxima. Here we can say it is plus minus m, that is the order magnitude, plus 1 over 2, and of course it's going to be lambda here, you can say. Okay, let's just say this. Where's this? Okay, I'm looking for this button here. So we can say this one here, okay, 1 over 2 plus, 1 over 2, you could just say lambda, and that is, of course, what we have, you can say. Okay, now you can put this in bracket. If not, you could just put m plus 1 over 2. I think it would be better if I do that one. So m plus 1 over 2, that is going to be lambda here. So this is what we have. Take a look, but let me tell you something very important here. So what happens, normally we said this is basically m0 for the bright or central bright one here, correct? And of course the one or the bright one next to that, we call it m1, correct? But m1 for the bright one here. What about for the dark one here? What is the first darkest, or you can say fringe, that we will get? We will get it when, you can see that when the phase difference between the two is half. That means in this case m is 0, yeah? If m is 0, then of course 0 plus half, that is going to be half a wavelength, yeah? So of course we'll say d sine theta, it is equal to half a wavelength, correct? If that is the case, of course, then we will get the first dark fringe here. But remember this, there's something very important here. So when m is 0, we get the first dark fringe here. So this is the first dark fringe when m is equal to 0 here. So whenever it comes to the order of magnitude and the number fringe, for bright one, you don't have any problems. But if it is mentioning the dark one, you always have to take one less, let's say, compared to the number of, let's say, the fringes here. So for example, when we say the first dark fringe, that means m is 0. We'll go through the detail as well, but just remember this. When we say the second dark fringe, m, that means m is 1. So you can always go with m, or the order of magnitude for dark fringes only. It is always one less than the number of dark fringe. So like I said, if they say the first dark fringe, that means m is 0. The second dark fringe, m is 1. The third dark fringe, m is 2, and so forth here. Okay, so predicting the location of the interference fringes, I did, I've almost like talked about this one here, but I did not talk about the detail, or why do we call this one d sine theta, yeah? So we said we have an equation. If one of the wavelength, for example, let's say travels this much, okay, the other one travels a bit extra, yeah? But this a bit extra, I just said it is, basically we call it d sine theta, yeah? Okay, so d sine theta, that's what I said, equals to, let's say, plus minus, if it is for bright, m times the lambda here. And of course, this one here is called path difference. But where does the path difference comes from? We said one wave, let's say just this one here, it is traveling a distance of L. The other one is also traveling another distance, let's say, but let's call this one L2 here. That is the distance that this wave is traveling. But then one of the waves is traveling a bit extra than the other one, correct? Now this bit of extra, let's say, we said it is basically, if it is a whole number of wavelength for bright fringes, of course we get constructive interference. If it is half a wavelength, that is destructive interference. But this extra half a distance, you can say, or this extra distance, it is called d sine theta. You can call this one path difference as well. So this part, it is called path difference. Path difference. But if it is for bright, it becomes this. If it is for dark, of course it becomes positive, negative. You can say 1 over 2 plus, or m, let's say, m plus, that is order of magnitude, 1 over 2, let's say lambda here. So this part, that is for bright, this is for dark, and this is called path difference. But if this is called path difference, isn't it the same or equivalent to these two as well? So if you are given d and sine theta to find path difference, you can use d sine theta. If you have n and lambda, or those, for example, and you've been asked to find path difference, you can say path difference is also equal to this much. So whichever the side of the equation is given, you can use that to find the path difference here. But why do we call this one d sine theta? Well, that is very simple. If you take a look here, we have a 90 angle here in between, or you can say a right angle here. So this angle is theta, this is the distance basically, and this, you can say opposite of this. And of course, you've studied in math that the sine function, if I want to know, for example, what is opposite here, we can call this one opposite if you want to. Okay, so this opposite, it is basically, here's the theta. So we'll say sine function, sine theta equals to what? Normally equals to hypotenuse, that is the hypotenuse, which is equals to the opposite over hypotenuse. You do know that, but the hypotenuse here, it represents the distance, which is the distance between the two slits here. So once you cross multiply, so opposite here equals to d sine theta. So this opposite, or you can say this extra distance, which we call the path difference, it is equal to d sine theta, and this is where it comes from. So this is how we can find this d sine theta using this angle and this distance using sine function. Anyway, but perhaps you might not need to know this, but just remember this, d sine theta is called the path difference. So what is, or how we can define path difference? We can say path difference is the difference in the distance traveled by two beams when they are scattered in the same direction from different points here. Okay, so that'll be the definition for that. Now we have also another question, says what? Why is the central maximus always bright? We said the central maxima is always bright because the two waves will always cover or travel the same distance. So whenever they land, whenever they reach the screen, they both have covered the same distance. Once they cover the same distance, that means they arrive in phase. And if they arrive in phase, will that be a constructive or destructive interference? Of course, it is a constructive interference. So of course, it is always bright, or you can say the brightest among the other fringes, or compared to the other fringes. Okay. Now, we have a few study tips. The first one says, the value for the path difference determines whether two waves are in or out of phase when they arrive at the viewing screen. So we've went through this one here, but this is of course the detail of that. We'll say, like the path difference of the two waves when they arrive on the screen would tell you whether, okay, these two waves will, once they land on the screen, will form a constructive or destructive interference. We said, if the path difference that is equal to a whole number, let's say m times lambda, so a whole number times the wavelength, or if the phase difference between the two, watch this, we have path difference and phase difference. If the path difference between the two is 1 lambda, 2 lambda, 3 lambda, 4 lambda, as long as it is a whole number of multiplied by lambda, that'll be a constructive interference. Or you can say, instead of saying the path difference, you can say if the phase difference between is, let's say 0 pi or 2 pi, or let's say 6 pi, 8 pi, in this case, of course, we get a constructive interference here. So that is basically how we can tell if, or basically the path difference will tell you if the two waves will form a dark or bright fringe here. So this is basically, we can say, the condition of a constructive interference. White fringe will be produced, but when? If the path difference, what was the path difference? D sine theta. If d sine theta, it is equal to 0 or some whole number of multiple of the wavelength, of course, we can say, let's say, if the path difference is 0, for example, or if it is 1 lambda, I forgot to mention 0 earlier. If it is 0 or 1 lambda, 2 lambda, that means we have a whole, let's say, the phase, or just like the phase difference between the two is either 0 or this, or the path difference is 0, that means both waves have traveled the same distance. If they have traveled the same distance, they will arrive in phase, and of course that would lead to a constructive interference. Okay, so we can say if the path difference is 0 or some whole number of multiples of the wavelength, 0 and all that, the two waves will be in phase, and of course that is what causes a constructive interference. So how do we write that as an equation? We will say equation for constructive interference equal to d sine theta plus minus, we said this plus minus indicates the number of fringe, the number of, you can say, m, that'll be the order magnitude, yeah? If it is above, you can call it positive, below, call it negative, that's not a big deal, and then multiplied by the wavelength. These are basically the condition of, or we get constructive interference as long as m it is equal to what? equal to 0, 1, 2, 3, and as long as it is a whole number. So remember this? We said we call this part path difference, which is, so once again, this part is called path difference, but this is also equal to this. So whichever side you have to find the path difference, go ahead and do that. And of course, these are the information. D is basically the slit separation measured in meter, since it is a distance. Theta is the angle of diffraction, which is basically between the fringe and the central fringe, you can say, or fringe, let's call it, measured in degrees here, okay? So m is the order number, lambda is the wavelength measured in meter, of course. So we said when the angle theta, it is 0, that means m is 0, it's called the 0th order maximum here. Or you can call it the central maximum, which is basically the brightest. The first maximum on either side of the central maximum, which occurs when m is 1, is called the first order maximum, and so forth. We have m2, m3, and of course it goes on. So how do you define the order, let's say order number, or m? We can say m is the number assigned to the interference fringe, all right, fringe with respect to the central bright fringe. So take a look here. We said, remember, if these two cover the same distance, the path difference is 0. Okay, then of course we'll get a bright fringe in the middle, that is the central bright fringe here, or central maxima here. But if, for example, if we take the one right next to it, you can see that these two arrive in phase, yeah? So if you take a look at this one here, the next bright one, okay, so one of them traveled one, or just the distance L, and the other one traveled this distance plus one whole wavelength. So of course, once again, they arrive in phase, we get another bright fringe. And of course, if you look at this one here, there's the central maxima, or 0, first maxima, second maxima, or you can say m1, 2, 3, that is above, and of course, we have the same thing below as well. Okay, now, the second condition, for example, that we have, once again, we said d sine theta, that is the path difference, determines whether the waves are coming on the screen will be constructive or destructive. So the first part we said it will be constructive as long as we have a whole number 0 or a whole number, let's say multiple of wavelength here. What about the second case here? That is number 2. We have destructive interference, remember, or you can call it dark fringes, will be produced. But when? It will be produced if the path difference is an odd multiple. An odd multiple of what? An odd multiple of, let's say, or half a wavelength, you can say. So what do we mean by an odd multiple? So for example, we have an odd multiple or half a wavelength, yeah? So we'll say, as long as we have odd numbers, we can say 1 times this, yeah? Or the next odd number that we have, it is going to be 3 times this, yeah? So of course, it will be, let's say, 1 over 2 wavelength, 3 times this, that is going to be 3 over 2 lambda. The next one, that is going to be 5, right? So 5 over 2 wavelength and all that, yeah? So these are, you can say, odd multiples, yeah? So these are odd multiples of this much here. So once you do this, of course, you get odd, you can say, wavelength here, or not a complete one here. If that is the case, then when the two waves arrive on the screen, they will be out of phase by 180 degrees. And if that is the case, of course, they will interfere destructively. We will get a dark fringe here on the screen, okay? So what is the condition or the equation for destructive interference? We'll say d sine theta, that is still the same path difference, but what is different here, it is m plus 1 over 2 lambda. If you remember, for constructive, we just said m lambda, yeah? But to make it destructive, we'll have to say plus half a lambda, because this half a lambda, it makes it 180 degrees here. So you can say 1 times this, or of course you can say not 2, of course 3 times this, or 5 times this, as long as it is, let's say, not this one here actually. Okay, so we can still multiply by half. What did I say here? Okay. Not this one here. So in order to make this one correct, okay, we can still use m as a, like whole numbers here. But the reason why we have this, because this half a wavelength, no matter what the multiple is, it will always make the phase difference to remain 180 degrees. And if that is the case, of course, the two waves will always be out of phase by 180 degrees. And of course, we will always get a destructive interference. For example, let's just say if m is 1. So what do we get? We'll say, of course, now 1 plus, let's start with 0 first of all. If it is 0, what do we get as a result? Of course, we will get 1 over 2, 0 plus 1 over 2, that is still 1 over 2 wavelength. So if it is half a wavelength, that means the phase difference that is 180 degrees between the two waves. They arrive on the screen out of phase by 180 degrees, so this is a destructive interference. We'll get a dark fringe here. What if we use 2, for example, here? And of course, that is, we can say, if you use or find the common factor and all that, or you could just go ahead and multiply this. So imagine this is 2 as a whole, so 2 times 2, that is 4, plus 1, that is 5 over 2. 5 over 2, we get what? We get 2.5 wavelength? Okay, so that is basically, we will get 5 over 2, let's say, wavelength. Now that is not a full number or complete number, let's say, of a wavelength. And once again, once the wave arrives on the screen, we still get 180, let's say, phase difference. And if that is the case, the two waves will always interfere destructively. So I hope you got the idea here. But like I said, it's very important to know this. When m is 0 here, we will get, when m is 0, let's clean this. When m is 0, we get the first dark fringe here. So if this is the central bright one, here's the first dark on one side, the first dark on the other side here. So if m is 0, we get the first one here. So we can call the first dark fringe here when m is 0 here. So that is why you really have to be careful when it comes to naming these and considering or calculating m as the order number. When we have the first dark fringe, the value for m, it is going to be 0. When we have the second dark fringe, m will be 1. When we have the third dark fringe, the fringe, m will be third one we said, so m will be 2. So we can say the value for m is always 1 less than the number of dark fringes that we have. So let me ask you a question. When we say the 7th dark fringe, what is the value for m? It is going to be 1 less, which is going to be 5 or 6 or 8 perhaps, yeah? No, it is, okay, I said 7, yeah? So in this case, m is going to be 6, which is 1 less than that. I almost forgot what I was asking. Okay, so that'll be strength though. Okay, what do we have in here? So here's the equation that we have. Don't forget, m still 0, 1, 2, 3, 4, and all that. You can say it is a multiple, or you can just say whole numbers there. Okay, where m is the order number, wavelength is measured in m, meter, that is all that. Okay, so if m is, take a look at this, if m is 0, then of course we get plus minus half a wavelength, phase difference is 180, we get the first dark fringe, fringe on both sides here, yeah? So if we assume that these are the bright ones, okay, this one here is a bit dark, you can consider those to be the, let's say, the dark ones, yeah? That is in between the bright ones. If m is 1, of course, the path difference is going to be 3 over 2 here, which is basically the condition for the second dark fringe and on. I think I've just jumped like from 0 to 2 immediately. Okay, the previous example. So the numbers indicate two maxima, the purple maxima you can say, that are either, or from, let's say, on either side of the central maxima, or 0th center maxima, or you can say 0th order maxima. The darkest areas indicate the position of the dark fringes, or minima. By the way, sometimes we call it minima instead of, so we have maxima, maximum brightness, minimum, minimum brightness, you can say. The plural of minimum that also appears in the pattern. Okay, now we have a question. I think we need some questions because that was too much explanation. It says, interference in sound is recognized by difference in volumes. So when interference normally happens in sound, we get constructive and destructive regions, yeah? For those regions that are constructive in sound, the volume of the sound becomes louder. For those regions that we have destructive, the volume of the sound is either going to be lower or complete silent, let's say, if it is completely destructive. But how about light, for example? How do we see, or how is the interference in light recognized? How do we notice that? We'll say if it is light, we can see or recognize by the presence of bright and dark fringe. If it is bright, that means, we have constructive interference. If it is dark, that is clearly destructive interference. Okay? Now, take a look. We have another question. Says, a double-slit interference experiment is performed with red light and then again with blue light. In what ways do the interference patterns differ and says consider the difference in the wavelength for the two colors of light. Well, I think that's obvious because I've mentioned, I believe, in one of the lessons. I think it was the previous one. Yeah? So if I watch this one here, so let's say, how about if I minimize this a bit? Okay, so watch this. Let's say here's the screen, and here's the, let's say the slits that we're using here. So of course we have different what? Or we can say this is the central bright one, correct? First of all, we're going to do it with red here. So here's the equation. We'll say d sine theta is the path of fringe equals to what? Equals to plus minus. Let me just go with m lambda. Ignore plus minus here. So we said this sine theta is basically the angle between the central maxima and, of course, the bright fringes here. If this is for red here, so for red, we do know that red has a, let's say, longer wavelength compared to, what is the other color? Blue color, yeah? So red has a bigger wavelength. Bigger wavelength, that means this sine angle or this deviation, of course, is going to be bigger. That means if this is for red, we expect something to be like this one here. But if I use blue, since it has, let's use blue, let's say. If it is blue, since it has, I should have used red color for this, so let's go ahead and use red. Let's say this is for red. I think I'm happy with this. We'll do this one again. So let's say here's the screen. Here's the slit separation and all that. So this is the central. So, and then if we use red, we expect a big angle here because why? Because you can see bigger wavelength, that means bigger angle here. But if we use blue, of course, because the wavelength, this is for red, this is for blue. It has a lower, or you can say smaller wavelength. Smaller wavelength, d sine theta. So smaller wavelength, obviously smaller angle here. So we expect something here for blue. These are both, by the way, M1, you can say M1, yeah? So what is the difference between the two? This is M0. These are constructive, as you can see. So we'll say, because the wavelength of the red color is bigger than the blue, red light will produce a more spread out pattern, while blue light clearly produces a more compact pattern with more fringes as well. Why? Because if the angles are, or the, let's say, the interference are closer together, of course you have more space for more, let's say, bright spots on the screen as well. But if the angles are, or if the spots are very far from one another, of course you don't have enough space for all these bright spots on the screen, you can say. That is just, like for the sake of an example. Now, how do we summarize what we have studied for both constructive and destructive interference, let's say in a page or two? So basically, what you see now is, or what we are about to do is, we're going to summarize the conditions for both constructive and destructive interference, or basically for what we have studied so far. So it's truly important to understand this. Once you understand this, you might not need what we have went through so much. Okay, well, what I have explained here. So conditions for bright fringes here. Okay, so for example, we said these are basically the order number, path difference, and phase difference. There's a difference between path and phase difference, yeah? When we say path difference, that is, we are talking about, for example, the wavelength. But if it is the phase difference, that is the angle between, or you can say the correlation between the waves here. And then, of course, or yes, you could say that. And then, of course, we have the fringe number, which is basically, you can say which one it is, yeah? First, second, and all that. So when m is 0, basically, that is, we're talking about constructive, by the way, or bright ones here. When m is 0, the path difference is 0. Why? Because we are basically using this equation. So if you use this equation, if m is 0, that means, of course, we have you can say the path difference. Here's the path difference, d sine theta. So when m is 0, you can say the path difference is basically going to be 0 here. Because now if m is 0, path difference is 0. And then, of course, the phase difference between the two is going to be 0 as well. The phase difference, yeah? And then what do we get? We get, as a result, we get central bright fringe here. That is for constructive interference. What about when m is 1 here? When m is 1, the path difference becomes 1 lambda, correct? If that is the path difference, then what about the phase difference? It becomes what? It becomes 2 pi here, okay? Becomes 2 pi. And if that is the case, of course, we get the first bright fringe here. So if we go here, if this is the central here, So let's say this is the first, and of course we have the second. That is on either side, by the way, here. So you can call these are positive, these are negative. We just go through the positive one for now. Okay, now what about when, for example, when m is 2? So put 2 here, that is 2 times the wavelength. Of course, plus minus, so on either side here. And then d sine theta equal to 2 times the lambda. If that is the case, we'll say 2 times the lambda, or you could just say, remember, each phase difference, if it is going to be for constructive 2, so you can say multiple of that, yeah? So 2 times 2, you can say that is going to be 4 pi, correct? And then, of course, we have 6 pi, and of course, we have 8 pi, and it goes on and on. Okay, as long as it is an even number of pi, you can say. So 2, the path difference is going to be 2 lambda. The phase difference is going to be 4 pi, and of course, we get the second bright fringe here. So whenever I say the second bright fringe, that means m is 2 lambda. 2 lambda, each lambda is, you can say 2 pi, so it is going to be 4 pi here. So it's very important. What if I tell you, what will be the, what is the order number when the phase difference between the two is 6 pi? Remember, 6 pi, each 2 pi is one wavelength. That means it is 3 lambda. 3 lambda, that means you can say it is the third bright fringe, correct? Very good. I hope you understood the idea, because understanding this could save you a lot of time here. And of course, you can see the rest on the screen here. Okay, what about the conditions of the dark fringe? You have to be a bit careful here, because like we've mentioned, the difference between the number of fringes and also the m, or the number of, or the order, we can say the order number as well, because you have to be very careful. The equation for dark fringes, you can say d sine theta, that's the path difference, equal to m plus half, or 1 over 2 lambda, or you can say close bracket lambda, plus minus, of course, that's both up and down. Okay, so when the order number is 0, m is 0, we get what? We get the first, is unlike the other one, okay? Unlike the other one, because the other one, when m was 0, the path difference was 0, the phase difference was 0, we got the central. But here it's different, because we already have central, which is bright. So when m is 0 here, we get half a wavelength. You can say the path difference is going to be half a wavelength. But then if that is the case, so the phase difference is going to be just 1 pi, or 180 degrees. If it is 180 degrees, we get our first dark fringe. So you see, the order number is 0, but the number, or fringe number, it is going to be 1, or first, yeah? The first one. What about when m is 1? When m is 1, of course, we get 3 over 2, and that is basically 3 pi, you can say. By the way, you could just see 3 over 2, 3 pi, yeah? 5 pi, that is 5 over 2. 7 pi, 7 over 2. So you can see those, yeah? Hopefully that helps you to see the connection between all this. So if m is 1, we get 3 over 2. You could just use 1 here, and then of course, that is going to be 1 times 2 plus 1, that is 3 over 2. Okay, lambda. That is the path difference. For the phase difference, we said it is going to be 3 pi. If it is 3 pi, then we get, remember, m is 1, while the number, or the fringe number, is going to be the second. So we will say, remember, because you'll need m in the equation, so more likely they'll give you this, and you'll have to find m here. So remember, m, the number of order, is always 1 less than the number of fringes here. So like I said, if I say the third dark fringe, that means m is 2. If I say the first dark fringe, perhaps this is the point where you might make mistakes out, because it says the first here, you might just go ahead and use m equal to 1, but no, it is always minus 1. So the first dark fringe, that means m is 0, because you'll say 1 minus 1, that'll be 0. We said always number fringe minus 1 to get the order number. And once you summarize or master this, inshallah, you will have no problem later on. We have a study tip regarding the m and all that. It says what? For the dark fringes, the order number m is always 1 less than the fringe number seen above. For example, when we say the first dark fringe, m is 0, so we get half a wavelength. When we say second dark fringe, m is going to be 1 less, which is 1. Third dark fringe, m is 1 less, which is going to be 2 here. Now let's get into some calculations. So that's example, that is sample problem, the 7a. It says the distance between the two slits. We did mention that. We said the distance between the two slits, that means d, yeah? Very good, which is basically 0.030 millimeter. We're going to convert that into meter, times 10 to the power negative 3, very easily. says the second order bright fringe. So as long as it tells you bright, that means you don't have any problems. You just use exactly or whatever that is given into the equation and then find whatever that is been asked. So let's say this is what we use in here. All right, but we cover this one too. Not this. Out of curiosity. Okay, so doing this too. Okay, so take a look. What do we have? It says D, that is the distance between the two slits. It is basically 0.030 millimeter. Each milli is 10 to the power -3, that is in meter. Okay, it says the second order bright fringe, so M is going to be second, that is this. As long as it is bright, so we don't have any problem. Is measured on a viewing screen at an angle of, so we can say theta is 2.15 degrees, okay, from the central maxima, determine the wavelength of the light. So how do you find the wavelength, correct? Okay, so because it is the conditions for bright fringes, we're going to write the equation for bright fringes, let's say. So we said d sine theta equals to what? Equals to plus minus m lambda. Let's forget plus minus here, just m lambda. So we want the wavelength, correct? So make the wavelength the subject. So we'll say wavelength equals to, let's get back to this. Okay. So we want wavelength, make the wavelength the subject. So wavelength equals to d sine theta over what? Over m. So what is d now? You plug in the numbers. D, it is basically 0.030 times 10 to the power -3 meter multiplied by sine theta. That is going to be sine 2.15, okay, and then divided by the number of order here, which is going to be 2 in here, correct? You do the math, of course, you'll find the wavelength. But hey, don't forget, the wavelength you get is obviously it is going to be in meter, yeah? More likely, we'll measure like wavelength because they're too small, and most of the time we're going to measure them in, depends on actually, but mostly it is measured in nanometers, you can see. So let's take a look, see what is the wavelength in here. Not these, okay. So for example, you can see, you'll get a number, of course, in meter. You can always convert this meter into nanometer here, okay? That is easy enough. Okay, double check with the math or with the answer. All right, now take a look at this one here. This is pretty much the same idea with the other one here. But one thing you need to know is this one here. Take a look. The answer that you get is obviously in meter here. How do you convert meter to nanometer? You can always, you can say, because each meter is basically 10 to the power, if we convert meter to nanometer is bigger, so we can say multiply by 10 to the power 9 here. And of course, once you do the 2, of course, you get this as a result. So we converted meter into nanometer. This is what we get. Okay, so these are, just be aware of these small details. And of course, the rest will be easy. And of course, if we convert nanometer to meter, that is going to be negative, okay, 9. But if we convert meter to, it's almost like converting meter to, let's say, millimeter. If you convert meter to millimeter, you multiply by 10 to the power 3 positive. But if you convert millimeter to meter, that'll be -3. I expect you to know this. Okay, and another question that we have here says what? The same question. It says a pair of narrow parallel slits separated by a distance of this, that is d, in millimeter careful, is illuminated by a green component form of a mercury vapor. Lambda is given, that is in nanometer again. Calculate the angle from the central maxima to the first fringe on the either side of the central maxima. So you just, nothing there. You'll just plug in the numbers, and of course you will do that. What I want to do is a question like this. Take a look. What is the difference between this and the other one here? It is about a dark fringe here, our favorite question here. So using the data from item 1 or question 1, determine the angle between the central maxima and the second dark fringe. So whenever it says the second dark fringe, that means what is the order of m, or what is m? M, it is number of this minus 1. So if this is the second dark, that means m is going to be what? M is going to be 1 here. That is the only thing you need to know. The rest is, as you can say, as easy as you can say the previous part. But there is also another difference, which is in terms of the equation. Yeah? For the dark fringes, we say, or for destructive interference, we'll use d sine theta equals to let's say m plus 1 over 2 lambda. Close bracket lambda, same thing. Yeah? So let's solve this one and see how it goes. Okay. Then, all right, take a look. So what does it say? So in the previous question, if you go back, d was 2.05 times 10 to the power negative 6 meter. That is if you convert. I think it was after conversion. Okay, and then lambda, that is 5.82. That is times 10 to the power negative 7 meter. And then what? Once again, because the second dark, all right, so m is going to be minus 1, which is going to be 1 here. So what is the question says? Clearly find fringe interference. So determine the angle. Okay, so find the angle theta here. So write the equation. What was the equation? Say d sine theta, okay, equals to what? Equals to open bracket m plus 1 over 2 lambda, correct? We want to find this one right here. So I'll just send the distance between the two slits right into or under this. So we'll say, or perhaps I can do it in 2 steps. So sine theta, it is equal to m plus 1 over 2, and then lambda. It would be easier, actually, if you'd plug in the numbers and do the math, and then divide by the distance here. Once you find the answer, then of course we'll say sine or the angle theta, it is equal to sine inverse of the entire answer, and of course you will get the answer in degrees. So this is going to be the answer in degrees here. So you just plug in the numbers, do the math, and of course you'll find the answer. As easy as this, no more than, it cannot get more complicated than this. Okay, going through these questions real quick says, what data would you need to collect the correctly calculated, what data would you need to collect the correctly calculate, that doesn't make sense, but anyway, calculate the wavelength of the light in a double-slit interference experiment, yeah? So of course, if you write the equation, you will see that d sine theta equal to n lambda, yeah? So we need the distance or the slit separation between the two slits. We need the angle between the central maxima and of course the order, let's say, or the sine theta, which is basically the angle between whether the dark or the, the dark and the bright fringe, that is another one. And of course, we need, let's say, the order number plus the wavelength. These are all the information needed. Yeah? So we'll say you will need the slit separation, you will need the order maxima, and of course the angle of the diffraction as well here. To calculate the wavelength set, okay, so just make the wavelength the subject, then of course this would be the answer there. So once again, d sine theta, okay, equals to, let's say, m lambda. So if you want to calculate this one, you move the m here. So this is what it becomes. So you need the slit separation, you need the sine theta, that is basically the angle of diffraction, and of course the order number as well. Okay, that is what you basically need. That is the answer to this question. What about question 5 here? Says, if a double-slit experiment were performed underwater, how would the observed interference pattern be affected? And consider how light change in a medium, let's say with a higher index of refraction. That's a very good thing here. Okay, so take a look at this one here. There's some interesting one actually. So what is the relationship between speed of light in water compared to speed of sound in water? Do you know the answer? And I hope you do. Normally, for sound, the closer the particles, we can say the faster the sound can travel. So sound travel faster in water compared to air and the fastest in solids, yeah? But for light, it is the opposite. We can say the more the refractive index, in another way, the more the density of the material, the slower the light becomes. So if I ask you a question, in which medium the light is slower? Is it in air or in water? Clearly in water. So if that is the case, so of course we have C equal to frequency times wavelength. Frequency times wavelength. So clearly the frequency doesn't change. In water, the light slows down. If it slows down, that means the wavelength, of course, decreases. So if we use this equation here, d sine theta equals to m lambda, yeah? So if the wavelength decreases, what happens to the separation between the fringes here? So we can say if this is the separation, if this is the central, these are, let's say, first bright, second bright, and third bright, and all that. So if the wavelength decreases, the separation between the angles are also going to decrease as well. So you can say these angles, or you can say these fringes, of course, are kind of like clump up, if that is the correct word, or maybe get closer, compressed almost, or let's just use this word, I don't know, like a simple language. These would get closer to one another because the angle, the separation between the two, or those, will decrease. Why? Because we said frequency doesn't change of light, of course, by changing the medium. So the speed of the light slows down because you can say the wavelength decreases. If wavelength decreases, that means this angle must decrease as well. So you can see these two are directly proportional. If this angle decreases, that means the fringes will get closer to one another. So that'll be the answer. You can say the angle of diffraction theta gets smaller, leading to more closely spaced interference pattern because lambda decreases under water. Let's finish these two questions maybe. Assume that a white light is provided by a single source in a double-slit experiment. Describe the interference pattern if one slit is covered with a red filter and the other slit is covered with a blue filter. So if that is the case here, let's say we have white light, but then we have this. Okay, so one of them is red, the other one is blue. So will you see any interference on the screen? I hope you don't say no, yes, because these two have different frequencies. And if they have different frequencies, will they interfere? The answer is no, because that was the condition for interference. They must have the same wavelength, the same frequency. So two different colors, that means different frequencies, so no interference will be observed. So you can see, because waves are incoherent and of course have different wavelengths. That is the reason, or these are the reasons. The last one for now, interference pattern is formed by using green light and of course an apparatus in which two slits can move. If the slits are moved further apart, will the separation of the bright fringes in the pattern decrease, increase, or remain the same? It's also a very good question. We said real quick, d sine theta equals to what? Equals to m lambda. So, but what is the relationship between the two here? Aren't these two are inversely proportional? Because if you take sine theta as a subject here, you get m lambda over d. So there is an inverse relationship between the two. So by increasing the slit separation here, the angle between the fringes would get smaller. But if you decrease, let's say, the slit separation, then of course the fringes will separate from one another. So what is the question here? It says if the slits are moved further apart. So that means by increasing the distance. So if you increase the distance, what do you think will happen to the slit or to the fringe separation here? So of course you can see that. No, I should have erased the other arrow here. So by increasing this, then the you can say the fringes, of course, will get closer to one another. So the separation of the fringes will increase because theta is directly. What did I do here? It says what? If the slits are moved further apart, will the separation of the bright fringe and the decrease, increase, or remain unchanged? So if we move the slits further apart, and this distance gets bigger. If that is the case, then the angle between the two must get smaller. I'll have to double check with this perhaps. The separation between the fringes will increase because theta is inversely proportional with this. No, actually, it must decrease here. So please convert, or you can erase this one, make it decrease. Okay, make it decrease because, as I said, if we increase this one, there's inverse, or you can see these two are inversely proportional. So if you increase this one, this must decrease. So the separation between the fringes must decrease. So please fix this one if you have this booklet with you. So the answer is going to, or the fringes will get closer to one another. So this is basically, hopefully, we're going to end our session at this point here. Inshallah, next time we'll continue from question 9 and forward, inshallah. So till then, keep practicing, and I'll see you soon. Assalamu alaikum wa rahmatullah.